next speaker before the lunch is Christina Kelly. Christina is from LECO. LECO is our another sponsor who we thanks a lot for making this possible.
Oh, now can you hear me? No? Oh, now it's working. Okay. Okay, now can everyone hear me okay? We're clear? No. Now? All right, I can hear myself. Oh, there's an echo. Okay, so thank you all for staying for the last presentation before lunch. I'll try to make this quick so we're not, going into our eating time. Most of you are familiar with LECO, but just a little bit of background about us as a company. Before we were kind of one of the leading GC/GC commercial vendors, we actually started with rapid sulfur determination, or carbon determination, and then we made a sulfur analyzer, and we've been doing a lot of different analytical instruments since. Today, we're headquartered still in St. Joseph, Michigan in the US, and many of you have actually been to visit our facilities and done some training there. Highly recommend coming and seeing us there. You can see our demo instruments, and after you purchase, you can come and get some specific training for your applications needs. I work in the application team, and I guess we'll go through a little bit of history of some of the instruments. So we first started with GC-MS in 1995 when we saw from Kevin McNitt and Slava Artev that first fast analyzer. And we were able to then commercialize making the Pegasus instruments with the HRT with our folded flight path technology, then to our BT with benchtop, and then most recently with our new BTX, which is the next generation of our benchtop mass spec. And so, sorry, I think it's always interesting to see the picture and see kind of as time goes by all the different innovations that have happened in one lifetime, and just kind of the promise of what this technology can continue to bring. It's kind of fun to see kind of the next generation of scientists too continuing to work on this GC/GC time of flight mass spec technology. I want to take just a second to plug our BTX. It's our newest time of flight benchtop mass spectrometer. It's got a more rugged detector, and it's our most sensitive time of flight mass spec to date. And the sensitivity is really important, especially as we do non-target work, which is what I'm going to be focusing on with some of these statistical analysis tools in aviation fuels. So we talked about hardware. Now I want to talk about the LECO software offerings that we have. And one of the cool things is that because we develop the hardware and the software together, we specialize in this GC/GC multidimensional data, also the multi-dimensions of time of flight mass spec. And so we kind of have this beautiful marriage between this hardware with really great quality data that comes off, and then with software that was developed fit for purpose just to look at this type of data. And so we kind of have three flavors of Chromatoph right now on the market. We have Chromatoph, which is what you get with the instrument. It does the analysis. We control all of your auto sampler, GC, mass spec, your modulator, all of the parameters that you need for getting the sample data. And then also the basic characterization. So deconvolutions included. You can do target analyte find. You can do quantitation with calibration curves, classifications. I'll show you a really complicated web diagram that you don't really have to follow, but all the different options you can do with regular Chromatoph. Today I'll be focusing on Chromatoph Tile, which is our statistical package that looks specifically for differences between samples. And so we're looking at different statistical comparison tools like Fisher ratio, coefficient of variation, and fold change to look specifically at what are different between your GC/GC chromatograms. I'm touching right here on sync because that is another package that we have, but if you want more information on that, highly recommend you going to Liz Humston-Fulmer's poster this afternoon, and also to hear more about it at our beer tasting later tonight. But these software packages all have a little bit of a different bent, different purpose, depending on how you want to set up your experimentation. And they're all complementary approaches, depending on what you need. So this is that web diagram I promised you. In Chromatoph, you've had the full hardware control, as well as kind of if you follow that top branch, you can do classifications work, and I'll show a small example of that later. You can also do individual peak identification. So we're very peak table focused in this Chromatoph atmosphere here in native Chromatoph, where you can get your peak table with all the information, individual deconvoluted peaks that you can then create quantitations or targeted methods off of. And then finally, if you have a high resolution system, the ability to do some really cool spectral analysis tools work, which I think Joe showed in his poster yesterday. But again, you can come talk to us about any of those things if you're curious. So kind of an example of the workflow you would go through in general chromatoph, if you're just doing kind of basic characterization of a full characterization of a sample. You can acquire your data, do your automated peak find and library searches. You can then apply customized filters to search for specific analytes within the group that you get. So in this case, I think I applied a sulfur filter, said anything with a library similarity search over 800 out of 1,000. If it contains sulfur in the molecular formula, only show me those peaks. And so you can filter down and kind of get insights from your data in that way quickly, identify those analytes of interest. And again, we have the deconvolution that works well with GC-GC, built for purpose, beautiful spectra for every individual analyte as much as we can. But we can also do composite processing. So we've been seeing a lot of movement towards routine methods, doing this bulk group type classification work. And so we provide that solution in native chromatoph as well. So we get the peak information, but if you want to just summarize, what's the sum of all these masses, we can do that in these groups of templates that are generated with this kind of classifications approach. So that's native chromatoph. But I want to focus on chromatoph tile. So with chromatoph tile, like I said, we're looking at the raw data in this case, not deconvoluted, and we're trying to find specific differences. And so we're looking at the chromatographic space, breaking them up into little tiles, and using different statistics to determine differences. So the workflow is you input your data, and here I have different images representing types of jet fuel that we've received. You set up your data processing parameter, you choose which type of statistics you're going to use to look kind of for thresholds of differences. You can then compile those hits in a feature table. And so you basically get a result that says, okay, in this square part of your chromatogram, there was this number of masses that had this number of statistical differences. And so there's a lot of information there you can go through, pick, and choose, and say, okay, I want to select that as a feature that I think is actually important for this sample. And you can curate a feature table that you can then run more statistics on. And so you take that area of the chromatogram that's a mass with a peak potential, move it into a feature where you can then look at a library search that we use. Again, this is raw data, not deconvoluted, but you get a spectrum there that you're then able to putatively identify what something is. And then you can track it along your batch of samples and do statistics like PCA. So what are the three different flavors that we have with chromatoph? I think we released chromatoph 3 years ago, and that was with just the Fisher ratio, looking at class-to-class variation versus your within-class variation. And kind of that small image that you're seeing on the bottom tell you the kind of differences you can expect to see. So with the purple versus the yellow, you can see different kinds of Fisher ratios. You'd have a really, really high Fisher ratio in that first plot. And in the second one, you'd have probably a pretty low one because the class-to-class variation is pretty small, and but the within-class variation is really small as well. So it's a pretty high ratio. The third one, you're not going to see much because there's not much variation within class, but the class-to-class variation also isn't very big. And then that last one, your within-class variation is really huge, so that's not a meaningful difference potentially between your classes of samples. With the two other new statistics that we have now, coefficient of variation and fold change, you approach it differently. So with coefficient of variation, we don't care about what classes there are. You don't have to use them. You're just kind of looking at the standard deviation of those tiles, looking at the average areas, and you can kind of track trends in this way. Again, still looking for things that are different, but we're not saying belongs to group A, belongs to group B, looking at differences between them. It's just, we have a bunch of samples. They may fall into groups. There are going to be some differences. What are they? And one of the things about Fisher ratio that we needed before was replicates. And for fold change, that last option we have here, you no longer need that. We're really only looking at potentially 2 samples, and classes you can put in as well if you want to, but they're optional, and it's looking just at the max versus min responses. And so what does this meaningfully look like when you're setting up an experiment? So I was given a large batch of aviation fuels, and I was given some descriptors around some things I can talk about and things I can't. But the main thing that, for a Fisher ratio, it was I definitely needed classes. So one easy one was I knew some were traditional, pulled from the ground petroleum aviation fuels, and other ones were these new synthetic ones that are made from the new alternative or synthetic processes. And so using Fisher ratio to explore these is really great because there's going to be natural variation in the regular fossil fuel-based petroleum samples, and there's going to be variation as well depending on the processes used for the synthetic ones. Which things belong to traditional, in which things belong to synthetic, is something that Fisher ratios can help us answer. Whereas with coefficient of variation, we looked at just the subset of those synthetic aviation fuels. I knew there were multiple processes used, didn't know which processes were used for which sample, could kind of guess by looking at the chromatograms, but with coefficient of variation, I'm able to look and track some of those trends and maybe determine, which clusters belong to the same processes of samples. And then the last one was just comparing two samples, one synthetic fuel and another one that had an aromatics additive package added to it. And so using the fold change, we're able to pinpoint then right away what aromatics belong to the additive package just by looking at the difference using fold change. So again, the driving question for a Fisher ratio is what are the most statistically significant differences between these sets of traditional and synthetic aviation fuels? And so if you look here, what Chromatoph Tile was able to generate for us is an aggregate contour plot. And so on the top, you see what the traditional fuels looked like as a group when we averaged all of their masses in each tile. And at the bottom, you see what the synthetic aviation fuels look like. And so right away, visually, we can see some of those differences visually. But the cool part of having software is that instead of manually going through and looking at each thing, you can see here we set up the F ratio as our statistical threshold, and we're able to generate this hits table that we're able to look at a little bit more in detail. You can also set up library searches, so with each individual tile, then you can do a library search later for the features to see what each tile is. You can choose how to filter those hits if you only want to look within a certain retention time. So if you notice in the earlier chromatogram, there was a lot at the end that we really didn't need to see, so we could exclude the final end of the run because I know I'm not interested in that area. We don't need to spend any time delving into it. But this is the coolest feature, is the auto curation button. So if you don't want to spend a lot of time looking at every individual tile, deciding, yes, whether or not it's a significant difference, you can say, for all the tiles that are there, I want you to select the most differing mass, and then I want you to go ahead and just add that tile to my feature table. And so I did that if the F ratio meets a certain threshold. So I clicked auto curate, and I'm sorry, I'm going to show one more part of this, is you can individually, if you wanted to individually curate, you can go through and look at the spectra and make sure everything's correct for each sample as you go through. But when you click auto curate, you generate this new feature table now, which is populated with all of the different tiles with a mass that's already been library searched, and gives you potential identities for every difference that we see between these classes of samples. We're also able to track them with these nice plots, see differences throughout. And you can see kind of that blue section are traditional fuels, and the red bottom section is our synthetic fuels. It's very clear that this class of cyclic hydrocarbons are more prevalent in the traditional petroleum. What we can do with this feature table is, we still have, hundreds, if not thousands of features in this table. We can go through further and filter and find specifically what we might be interested in. So for me, I was curious. I wanted things that had a similarity score in the library greater than 800, even with just raw data. Looking for things that had a library match with a sulfur containing molecule. So when I say okay, filtered down to 3 potential hits that we can then add and display and highlight that, as expected, there's going to be more of the naturally occurring sulfurs in the traditional petroleum versus our synthetics. But you can also do more advanced filtering. So instead of just looking at something from a library search standpoint or area or any of these other peak parameters, you can specifically go into the spectra itself. So in this tile, I want there to be a base mass of 105 or a base mass of 120, knowing that there are specific aromatics that I might be interested in. So if I filter on just that criteria, we have a whole different set that we can focus in on and really look to see what differences in which compounds were of most interest. And so we can see here, this one's interesting. We've got the particular 1-ethyl-3-methyl benzene that is present also in the synthetic fuels, but in general, it's not in every process. And so once we've generated the feature table, we can go back and look at some PCA plots. And so if we look at that highlighted section, I'm zoomed in there, if you select the statistics button, you can create a PCA plot using either all the features or specific features you've chosen, and then perform the PCA, including as many samples as you prefer. And so here we can see I included all of the samples. I just used all the features just curious to see what we could do with the automated version of everything. And we can clearly see distinct clusters of our traditional and our synthetic aviation fuels. So that was using the Fisher ratio. The next experiment was looking at this coefficient of variation. And so again, the driving question here was, what kind of major chemical variation do we see between the processes, and can we see clusters of similar processes? Here we didn't use a statistical threshold, but we used a relative change threshold to apply. So coefficient of variation and Fisher ratio can be used in conjunction in tile, but for simplicity of the story, I left with one statistical method for each one of these case studies. But I knew the possibilities were great for all the different types of processes that could have been used for these synthetic fuels. You have your Fischer-Tropsch synthetic paraffins, low temperature, high temperature, things with added aromatics packages, HEFAs, synthesized isoparaffins, the alcohol to jet, bunch of different types of things that were possible. And so I figure with this kind of variation, we're going to see a lot of differences. And right away, from the HIT roadmap, or the HIT heat map, you can see that there is a lot more variation. They don't cluster as nicely into kind of distinct classes. But I was still hopeful, and so using the auto curation feature, transferred all of the features over to a feature table, and then again used the auto PCA. Used the auto PCA and was able to generate a couple of distinct pieces potentially. So we can see that those on the farthest right at the bottom, seems like that might be one process that's different than kind of that middle cluster of processes that are more similar to each other. So for the final case study I'm going to go through today is looking with fold change. When you only have two samples, you don't have replicates, and you just want to see quick differences. And so in this case, the question is, can I look at which compounds make up my aromatics additive package? And so again, when you set up the processing method, the only thing we change here is to look for the relative change threshold type using that log base 2 fold change as our statistic test. And we can see here, we are generating really nice average plots for our, well, it's not an average plot because it's really just one sample. You can see our difference in our chromatogram, really. And then some of the places that tile has picked out little black dots that indicate areas that may be of interest with different masses. And so with that auto curation of our hits, we have a feature table that we can easily go through, look at spectra for different tiles, and pick out potential aromatics that are what make up those additive packages. And all relatively quickly. So processing time with this raw data is much easier for the computer than deconvolution. And so we're able to very quickly do these statistical tests and help us pinpoint areas of difference that we're interested in. So hopefully, with this kind of quick overview, you guys have been able to see that there are a variety of different processing methods that are available, and choosing the right one will simplify answering your question, whether it's from a non-target characterization of every individual peak or looking at specific areas of interest. And I hope that you'll be able to see soon more about Sync and Sync 2D, where you can use aligned peak tables to look at this information. So with deconvolution, looking at similarities and differences together in one package. Just another plug for our beer tasting tonight. Hope you'll all come out and chat with us. We welcome you at 6 p.m. at the Salle de Professeur. And we have also a plug for ACS Fall in Washington, D.C. I just want to encourage all of you here, if you love GC by GC, you have more work you want to present, we would love to have you submit an abstract. The deadline is March 31st. And Peter Voska and Kate Pro are also helping to organize this, and we're hoping for 2 days of presentations. And there's a lot of interest from multiple dimensions, from the energy and fuels division, as well as the analytical division of ACS. So highly encourage you guys to submit presentations for that. Thank you for your attention.